Hello, good morning, good afternoon, good evening, wherever you are in the world. I'm very honored to have the opportunity to talk to you today about Java's new concurrency features. So my name is Hanno Embregts. I work at InfoSupport as an IT consultant, and I'm really passionate about Java and the new features in Java that recently came out, which is why I'm talking to you about them today. So I want to talk about concurrency today. And I actually got the idea for this talk while I was out for some drinks with some friends on a Friday night. We were in a bar, and the waiter came up to us and said, "Hey, do you want some drinks?" And we were like, "Sure. What do you got today?" And he said, "Yeah, we don't have them printed on a menu." So he just listed a few drinks, right? And we just let him talk for a while. So he listed, in the end, he listed about 15 or 20 drinks. And when he was finished with his list, we were like, "Yeah, okay. What was the first drink that you told us, right?" So he was kind of a bit disappointed, like, "You've made me talk here about our drinks for a few minutes, and then you want the first one, right?" And while this was happening to us, I was like, "That is such a good idea for a concurrency talk, right? If you spin off multiple tasks in the background, but you already know that after the first one completes successfully, that you have the final result that you want, why would you still wait for other tasks to complete? That's just a waste of time, a waste of processor resources, and you could just cancel those tasks." Well, as it turns out, with the new concurrency features that were published in Java 21, we can actually cancel those tasks in the end if we don't need the result anymore. So that's a sneak preview of where we're headed in this talk. And I'll also demo those capabilities, of course. But first, I want to take a step back and see what concurrency features Java currently offers, because Java has been in a journey towards better concurrency features since the very beginning of the language. And if we take that analogy a bit further, you could think of it like a train journey, right? And you get in at the classic thread station, and you move along many stations, like ExecutorServices, CompletableFutures, right? Thread local variables, until we get to our final destination. Or is it our final destination, right? That's a question that we'll get an answer to today in this talk. So just a very quick basic refresh of your memory if you've never seen concurrency in Java before. So the basic building block in Java's concurrency support is the thread class, which models a thread of execution in a program and which allows you to do multiple things at the same time, especially with modern CPUs with multiple cores. And we've been able to do this since Java 1.0, right? So let's see if we put threads to use in an example domain to see what behavior we would end up in. And I want to extend this restaurant and bar domain a bit further to be able to come up with a good relatable example, right? And the kind of restaurant and bar I'm thinking of is this one. Maybe it's familiar to you from your youth, watching Sesame Street with waiter Grover, who always did his very best to please the blue guy here, Mr. Johnson. But in this case, he ended up with a piece of Lego on his plate and, not the food that he ordered. Well, in the restaurant that we're modeling today with threads, all kinds of things go wrong, just like with the Sesame Street restaurant. So keep this image in mind, right? It's a restaurant where many things can go wrong. Now, if we model that restaurant with threads, we first define an interface restaurant that has an announced menu method and that returns a multi-course meal, right? So we are serving meals with multiple courses. And if we would implement that with threads, we would, for example, announce the menu, create a few waiters here, create a few specific threads that announce the courses, and each waiter then announces a different course, like Grover announces the starter, Zoe announces the main, and Rosita announces the dessert course. We then start all the threads and join all the thread to wait for the results, and finally we can create a new multi-course meal. Well, in this case, we have to extend the thread class. We're on Java 1.0, right, in this point of the talk, and we would have to have a dedicated getter to get to the result. Fortunately, starting from Java 5, we could also run callables that return a result, so we wouldn't have to specifically subclass the thread class in this case. But this is the basic building block, right? Well, the pros are you can do multiple things at once with threads, but the cons, like I said, you can't return a value directly, and this can be done from Java 5 onward. And also, one thing that I don't like is the unit of work and the mechanism to run it on are one and the same. It's a thread. You cannot schedule work somewhere and let it wait until there's a thread available. You have to tie the unit of work to the thread here. So that's not very flexible. That is also what the Java language designers thought. So then came the executor service, the next station on our journey, that simply executes tasks that you submit to it. And this construct supports task queuing. So you can submit multiple tasks to it, and it will just try to process them one by one according to a specific scheduling mechanism. Also since Java 1.5. If we would change up our example with threads and replace it to use an executor service, it would start to look a bit like this. I'll just highlight a few lines of code here. So here at line 8, we can create a new executor service here, store it in the executor variable, and we can, for example, configure it to use 3 threads. But we can also change this number, right? 5 threads, 2 threads, whatever we want. So now we have separated the unit of work and the run mechanism. We can also use a cached thread pool if we want, that just creates a thread for each task that we submit to it. Then the actual work is done here. We submit, in this case, callable lambda expressions to the executor service, and we get futures back. And if we want to get the results, we call blocking get operations on these futures. Those will yield the 3 results and allow us to construct a multi-course meal. That looks good enough, right? Looks workable. But what if you sit down for a 3-course dinner and the chef picked out the menus, but then discovers that one of the ingredients is out of stock, meaning that one of the courses cannot be served today? Well, if we would model this in our code example as the fact that the announced course method can now throw an exception, an out-of-stock exception, I don't think the piece of code is still good enough. For example, if this line of code takes a long time to execute, and in the meantime, the announcement of the starter course fails because of an ingredient that is out of stock, then the entire method, the announced menu method, will wait for this main course announcement by blocking on the main.get here. But we already know that we cannot construct a multi-course meal because the starter is not available. So it's very wasteful to wait for the result here. Secondly, if an exception happens in this line of code, so in announced course, then it will be thrown by the main.get call. But the other announce calls, the other threads, will continue to run even after this entire method has failed. So that's also a bit of a waste. And finally, if the thread that executes this entire method announced menu is interrupted, this interruption will not propagate to the 3 subtasks. So they will just continue to run, even if this method has been interrupted before. So all these threads in line 9 to 11 will then leak because they continue to run even after this method has failed. So ultimately, our problem here is that this program is logically structured with task-subtask relationships, because we need 3 completely assembled courses to return a multi-course meal. But these relationships only exist in the mind of the developer and not in the executor service mechanism. Executor service is based on unstructured concurrency. And that's a fact that we just have to accept at this point. So the pros of executor service is that the task can directly return a value. Like I said, we've separated the unit of work and the run mechanism. But the cons, we will always wait for all tasks to terminate, even if one of them has failed or is canceled. And also when we know for sure that the desired result is not achievable, executor service will still wait for all tasks to terminate. To summarize, it allows unrestricted patterns of concurrency. In theory, one thread could create an executor service, a second thread could submit work to it, and the threads which actually execute the work would have no relationship to either the first or the second thread. I like to call them one-way jumps. And I also like to compare them to the notorious go-to statement in the basic language. You just transfer control to a different part of the program, but you have no way of knowing if it will ever return to the same place. And this is what I mean by unrestricted patterns of concurrency. So another station in our concurrency journey is thread local. This is a variable that is unique to its own thread, and each thread then has its own independently initialized copy of the variable. You can use it as the equivalent of a global variable in the threaded world. So imagine you need a value in many places, and if you want to avoid cluttering up your method signatures by passing it around everywhere, you could use a global variable, at least in the non-threaded world. In the threaded world, such a value would be unique to each thread, and you don't want to clutter your method signatures again. So in this case, you could use a thread local. It is available since Java 1.2. For example, what if we would want to uniquely identify each announcement by each waiter? We could then generate an announcement ID, right? This is an example class that generates such an announcement ID. It is assigned the first time that announcement ID.get. So this method is called, and it is assigned with an initial value, right? And there's an atomic integer behind that. Every time the get is called, it is incremented for a new thread. And so each thread here holds an implicit reference to its copy of a thread local variable, as long as the thread is alive and the thread local instance is accessible. After the thread terminates, all thread local instances are subject to garbage collection, of course. And if we would want to use this in our announcement, we could, for example, in the waiter class, we could just refer to announcement ID.get here. And also in the chef class, using the same announcement ID.get. And because these methods run in the same thread, for each announcement, we will get the same announcement ID value. So the pros here, it avoids cluttering method signatures in the threaded world, right? It's an elegant way to bind data that is unique to the current thread. You don't need any logic to achieve it. It's bound to the thread by definition. But a con is that it's always mutable. Any code that can call the get method of a thread local variable can also call the set method of this variable at any time. And in theory, it could have an unbounded lifetime, especially when threads live longer. So if you're using thread pools where threads may be alive for a bit longer, then thread local variables can ultimately take up a lot of memory, especially with inherited thread locals. So some thread locals cannot be inherited, but the inherited thread local class models an inheritable thread local value. And the way this is currently implemented in Java is that the child thread, so a thread that is spawned in another thread, the parent thread will copy the thread local variables from its parent and then add its own. Well, this is very memory intensive if you use that a lot. So there are a few cons also. So let's get to the question why this stuff even interests me. So my employer info support gives me the chance to combine Java consultancy with teaching courses. And one of the courses I teach is concurrency in Java. We have them up on our website also. And this is one of the reasons why I like spending time on the topic. Also, when new Java versions get published, I like to write articles about them. So I wrote a few articles on Java 20 and Java 21 on the Fuji.io blog website. And I encountered that there were many new developments concerning concurrency after virtual threads were introduced. So this is the reason I came up with this talk. Let's finish the introduction. So my name is Hanno. I work in info support. I'm both an Oracle ace and a Java champion. You can find me on Twitter, Mastodon, or Blue Sky at Hanotify. Also, if you have some questions after the talk that I didn't get to answer here, feel free to reach out to me. I always like that. And I tweet about Java development, concurrency, version control, sustainability, that kind of thing. So if you like that, make sure to connect with me. I really appreciate that. And now we're moving on to the next station on our journey, virtual threads. I mentioned it already. Virtual threads have been added to Java and have even been made final in Java 21. So how does that change the picture? So a virtual thread is a lightweight thread implementation, right? That means it doesn't have any explicit mapping to an operating system thread. And it is modeled in such a way that it's intended to run only a single task over its lifetime, which also means that the JVM has gained scheduling capabilities to make it run on a carrier thread. So each virtual thread, these are the brown circles here, can be associated with multiple platform threads over its lifetime, or a single one, right? We cannot know for sure. The JVM is deciding on which platform threads to run the virtual thread. Could be a single one, could also be multiple ones. We don't know for sure. So they may be executed by different platform threads or carrier threads. And still remains a one-on-one mapping between platform threads and OS threads. But of course, when we work with virtual threads, we don't really see this one-on-one mapping ourselves. I like to compare classic threads or platform threads to passenger trains or freight trains. They are expensive to create. They are quite slow to start. They are slow to stop. I'm not the only person who made this comparison, by the way. A lot of other important Java people made the same comparison. When I think of virtual threads, I like to think of taxis. They are cheap to create. They are fast to start. They are fast to stop. And you can have very many of them, like in this picture. So a quick sequence diagram to see why in what way virtual threads can perform better than platform threads. So this is a platform thread. Let's say we pull it from a thread pool and we fetch some data. So first some database data, then some data from a service. Finally, we send some data to a service, we get a 200 OK, and we're done, and the thread is released from the pool. Well, all these red areas is where the platform thread is blocked because we wait for results from the database or from the service, right? So we're waiting for I/O, essentially. If we would replace the platform thread by a virtual thread, this is what would happen. The virtual thread would actually show the exact same behavior as the platform thread. It would be blocked, but because the virtual thread doesn't have a one-on-one mapping with carrier threads, this time can be used for something else. So, for example, the first part of the job can be carried out in carrier thread 1. The second part of the job might be performed by a different carrier thread. We don't know for sure. But this also means that during these blocks, the actual carrier threads are free to run any other work, right? So all these dashed lines here mean that these platform threads actually are free to carry out any other work that is submitted to them. And as a result, the carrier threads or the platform threads are not blocked anymore. Just the virtual thread is blocked. But because the virtual thread only exists in the context of the JVM, the OS actually has far less blocked threads than before. And this significantly improves the throughput of your application, right? So especially with large weights on I/O, your throughput will be much larger. You could imagine many virtual threads here that take up the dashed lines here with other significant work. And what if you would want to use it? Well, with ExecutorServices, it's quite simple. You just change the factory method here to new virtual thread per task executor, and you can use it like you have used it before. And now we spawn a new virtual thread for each course announcement. You might already know this, but virtual threads can be created by millions, right? So millions of threads can run at the same time. Platform threads are limited in number because each platform thread comes with a stack that consumes by default 1 megabyte of memory, but the stack of a virtual thread is stored in the Java garbage collected heap as a stack chunk object. And these objects can shrink and grow as the application runs, which means that it's possible to create millions of them. And they also allow the thread per request style, which eliminates the need for thread sharing mechanisms such as thread pooling. And creating them and disposing of them is cheap and fast because we don't need the operating system to be able to create them. And like I already showed you there, you can achieve better throughput with a high number of concurrent I/O heavy tasks. But there are also a few cons, pinned threads. So there are two scenarios in which a virtual thread cannot be unmounted during blocking operation when it executes code inside a synchronized block or a synchronized method. or when it executes a native method or a foreign function. The OS thread cannot be unmounted. The virtual thread cannot be unmounted. If you would want to mitigate this drawback, you could replace at least the synchronized blocks, you could replace them with re-entrant locks or countdown latches. If you use them, you won't cause the thread pinning. And thread local variables don't really perform well with many threads. Like I said, they have a certain memory footprint when you use the inheritable variant of them. And this was foreseen by the Java development team. And actually, many thread locals were removed from the java.base module in preparation for the introduction of virtual threads, because they also saw this drawback. In fact, they even added a system property, jdk.trace virtual thread locals. When you set this property to true, Java will trigger a stack trace whenever a virtual thread sets the value of any thread local variable. So if you would want to migrate these thread local variables to something else, you could set this property to true to help you. So now that virtual threads are available, what drawbacks are amplified? What drawbacks become more significant? Well, I think this is the first one. The fact that the executor service allows unrestricted patterns of concurrency. It's very hard with executor service to create relationships among tasks and subtasks. And secondly, like I said, the memory intensity of thread locals. Well, is this then the final station of our journey? I don't think so, because the drawbacks that I just outlined are exactly the reason why Java's concurrency journey is continuing and trying to think of solutions to these problems. So as we're leaving our current station virtual threads, let's see what the rest of the journey has in store for us. Structured concurrency is the first feature that I want to talk about and show you. So this has been available in Java 21 in preview. If you want to work with it, you need to pass the enable preview compiler option to be able to work with it. And let's remind ourselves of the problem we are trying to solve. So do you remember this code example? I'm sure you do. Like I said, executor service is based on unstructured concurrency, but we would really like to use a hierarchy of tasks and subtasks. If we would consider a single-threaded version of this code, we wouldn't have any of the problems before. So in the single-threaded version, our waiter is called Elmo, and Elmo will announce these courses in exactly the right order. And if one of the subtasks failed, for example, the ingredient for the main course is out of stock, then the method will just end here, right? And the dessert won't even be announced. So the remaining ones won't even be started. So the structure of a single-threaded variant of this code actually would be very cool to achieve with multi-threaded code. And this is exactly what structured concurrency is trying to achieve. So it's an approach to concurrent programming that preserves the natural relationship between tasks and subtasks, which leads to more readable, maintainable, and reliable concurrent code. It was first coined by Martin Sustrick in 2016. He worked on Go routines in the Go language, and Roman Elizarov came up with the same concept. He worked on the Kotlin language, and it's called coroutines there. Or actually, inspiration was drawn from Go and Kotlin. I've put a graphic here to quickly explain what the difference is between unstructured and structured. So at the left side, we just spawn off new tasks, but we don't know for sure when they will complete and what the result will be. And with structured concurrency, we create a scope, which is the gray area. And before the scope ends, all subtasks must either be completed successfully or completed exceptionally. And then we're sure that everything is done. And you can create very complicated hierarchies using this method, as long as at the end of the scope, all tasks complete in the end, ultimately. So a scope continues until all child threads have completed, which results in a strict nesting of the lifetime of operations in a way that mirrors their syntactic nesting in the code. And this is a very streamlined error and cancellation propagation, which ultimately leads to improved reliability and observability in concurrent code. So to summarize, it derives from the simple principle that if a task splits into concurrent subtasks, they will all return to the same place, which is the code block of the task. I've got a few demos in this talk. I think we only have time for one of them, so let's get it out of the way immediately. I want to create a specific structured concurrency restaurant implementation and show you how it works. So here is my main restaurant code. Currently, it's configured to use a single waiter one. So let's create a structured concurrency restaurant here. And then my IDE will say, I don't know that class, so let's create it. It implements the restaurant interface. Let's implement the method that we need. And let's create a few waiters. We'll just use the same waiters we had before. So Grover, Zoe, and Rosita. Yep. Waiter. And then we start up a try block. We create a new structured task scope, and we want a shutdown on failure. And this scope, we want to, something is wrong here. I just forgot the new keyword. This is the demo effect, right? The demo effect. So we can fork a few subtasks here, and we can pass a callable. And in this case, it's just let Grover announce the course. Course type.main. Oh, sorry, he announces the starter courses. Let's fork another one. This is for Zoe. She announces the main courses. And then finally, Rosita will announce the desserts. There we go. We get return values, of course. The value of the type of the return value is a subtask, which is a specific type for structured concurrency, but it also is a supplier functional interface. That also means that you can call get on them. So eventually I want to return a new multi-course meal and call get on the starter subtask, which is also a supplier. Main.get, same thing, dessert.get. And the only thing we need to add right now is the behavior to wait for the results or wait for any exception. We can first call join. Optionally, we can pass a timeout, but in this case, I just call join, which means wait for all results to be available. Or if one of them throws an exception, well, throw an exception. In this case, we're just rethrowing the exception that the announced course throws. And this means that we're forking the tasks, and here we block until all of them are completed, or if one of them fails, which is the behavior that this method has. And if we get to line 23, we are sure that all results are available and that no exceptions have been thrown. So in this case, we get to a successful result. So I want to run this code, but first I have to show you something, and that is the course class. This is the class that creates courses, and when the chef chooses a course, it checks the stock, and each ingredient has a 5% chance of being out of stock. So if I run this multiple times, I won't see the same behavior each time, right? So what is then the chance that one of the courses will fail? Well, that is actually based on the implementation of the chef class. So the chef decides all the courses. Here they are. I've added a few of them. For example, lasagna is comprised of 4 ingredients, and each of them has a 5% chance of failing, right? So I just have to run it a few times, and eventually it'll fail. And then I'll show you the behavior that is displayed right here. So let's run the code and see what happens. We'll see some output, some announcements. Here you go. So the waiter introduced themselves. they talk to the chef to determine a starter course or a dessert course or main course. Here you see the announcement IDs. A specific course is picked, and then they are announced. Carpaccio, salmon, asparagus, potato gratin, and dame blanche. So in this case, all ingredients were in stock. But let's run it a few times again. Here we go. We have run out of raw beef. This means we cannot serve carpaccio today, which is the starter that was picked. So I can see output of waiters talking to the chef, but I don't see any output regarding the courses. And that is because the first announcement failed, then the other tasks were canceled because of the failure in the first task. But we still ran with multiple threads, so that means that the thread scope here decided that we cannot continue the work anymore. So that is the mechanism that is structured concurrency. So it uses short-circuiting patterns to avoid doing unnecessary work. So we have used shutdown on failure before. It's also known as invoke all, but there's a second subclass here, shutdown on success, which would elegantly solve the scenario I shared with you at the very start of the talk. I'll just skip to the finished code here. What if you are serving drinks to your guests, two waiters in this scenario, Zoe and Elmo, and they just start listing all beers we have in stock, all wines, all fresh juices, and another waiter is starting to list coffees, teas, cocktails, distilled drinks. Based on the preference of this guest, the guest can say, hey, I've heard a drink here that I really like. So you can stop listing all the other ones. Well, this is the behavior that is done, that is acted on by the shutdown on success scope here. So it will continue to run things until the tasks return successfully. So for example, if this guest really likes Pilsners and Zoe announces a Pilsner here, it will return the moment that she announces it, and the Elmo task will either not be started, or if it has already started, it will be canceled whenever it can, right? And then the result will be returned, and it's just a drink order. So shutdown on success does, in a way, does the opposite. It shuts down the scope and returns the result when the first subtask succeeds. This pattern is also known as invoke any. You can even create your own custom shutdown policies if you want. For example, collect all results that succeed and ignore all results that fail, for example. There are actually a few more use cases listed in the JEP. Let's see. The JEP that is about structured concurrency, so you should look that up if you are interested. So we now come to the section that I like to call sanity checks. Contains a few questions that I can imagine you have after hearing about all this. So wait a minute. At least Executor Service allowed me to pass thread configuration. I didn't see that option anywhere with structured concurrency. Does it support it? Well, in a way, it does support it. Structured task scope uses virtual threads by default, but you can pass a platform thread factory to an overloaded structured task scope constructor if you want. However, you should know that it is a deliberate decision to not allow thread pools with certain sizes, because structured concurrency performs best with a thread per request approach. So therefore performs best with virtual threads. Why do we need all these new scope classes? Why didn't they just enhance the Executor service to support structured concurrency? Well, the new class, structured task scope, enforces structure and order upon concurrent operations. And it doesn't implement the Executor service or the Executor interface, because those interfaces are commonly used in a non-structured way. So they opted not to change the Executor service interface because of backwards compatibility. However, I do expect that it is quite straightforward to migrate code that uses Executor service and that would benefit from structure to use structured task scope. You still have to migrate it. Doesn't ForkJoinPool also impose structure on concurrent tasks? Why would I then need structured concurrency? Well, that's true. Indeed, ForkJoinPool imposes structure on concurrent tasks, but that API is specifically designed for compute-intensive tasks. And structured concurrency is meant for tasks that involve I/O, waits and blocks. So it's a completely different thing in that sense. To summarize, virtual thread deliver an abundance of threads, and structured concurrency can correctly and robustly coordinate them. Scoped values, another station that we'll visit today. on our continued journey, or on our future journey, actually. But you can already use them today. Scoped values, they are in preview in Java 21. Again, you need to pass the compiler option, enable preview, to be able to work with it. And let's take a step back again, because let's remind ourselves of the problem that we're trying to solve here. Early in this talk, we added unique announcement IDs to our restaurant code with a thread local. What did we think about them? They serve to avoid cluttering method signatures, right? They are an elegant way to bind data unique to the current threads, but they are also always mutable, and they had an unbounded lifetime, especially with thread pooling. And they can also be memory intensive, especially with many threads or when inherited. So let's see if this newly added scoped values can help us out here. So scoped value is a value that is unique to a thread, same as with thread locals, but they can also be safely and efficiently be shared to method without using method parameters. So effectively, they are an implicit method parameter. So the purpose of them seems similar to thread locals, but there are a few improvements over thread locals here. They are immutable scoped values. They are written once and they can be read multiple times. They are comprehensible in the sense that they have a limited lifetime, and that lifetime is made very visible and clear from the structure of the code. And they can be robust. So data shared by a caller can be retrieved only by legitimate callees. Again, skipping the demo here and skipping to the final code result. So if we would introduce scoped values in our announcement ID class, we would do it like this. We would create a scoped value of type integer and initialize it here for a new instance. And we would probably come up with a way to get access to the scoped value from outside of the class, right? And if we want to use it, for example, this is actually the method in the waiter class that starts announcing courses. So this is the place where we need these announcements. We could just wrap this announce invocation here in a scoped value. So we'll just use scoped value.where. This is a method on the scoped value. We just pass the scoped value that we want to use, which is announcement_id.scoped_value. This is this method. And we pass it a value, which is, in this case, the return value of the next ID method. And then we use call, but there are multiple methods here, run for runnables, for example. And in this case, we pass a callable, so we use call, pass it a lambda expression. And the way this works is that this value is only available in the body of the call, which means any method that is called here, in this case, announce, will have access to this scoped value. But outside of this method, we won't have access to the scoped value, and actually an exception will be thrown if we try to get it. And this is the way that we get it if we can. Announcement.id.scoped_value.get will get us this scoped value. And again, in the chef class, we actually call the chef.pickCourse method here. So it's also within the scope of the scoped value. PickCourse method can use the same way to get to the scoped value, and it will return the same value and be able to relay this output line to the other one that was created by waiter. There are a few more features here. So scoped values are immutable, but it is possible to bind a new value to an existing scoped value. Here's a code example that I took from the JEP 446. If you start up a method called foo and you bind hello to the scoped value x, well, hello then will be available during this call, which is the entire bar method. So x.get will print hello, and here it will also print hello. But if you then rebind the value here, the value goodbye to the same scoped value within the scope of this lambda, which is the BAS method. In this case, x.get will print goodbye. But when this scope terminates and you get back to this point, x.get will print hello again. Right? So in this sense, it's still immutable. And it's like nesting scoped values in this case. Scoped values can also be inherited by child threads. And unlike thread local variables, there is no copying of a parent thread scoped value bindings. So scoped values in the parent thread are automatically inherited by child threads created with structured task scope. So in this case, scoped value.where binds 1 to drink order ID, right? And using structured concurrency here, scoped value inheriting is possible. So each task that is forked here automatically has access to this scoped value here. In this case, it is possible because structured concurrency can guarantee that a child thread forked from some parent thread scope will exit before the parent leaves that scope. And with legacy thread management classes, this guarantee cannot be promised. So that's the reason why these two features can work together very nicely. So should I migrate to scoped values? Are they always a better choice or just in certain situations? Well, I think you should migrate when your thread local deals with one-way transmission of unchanging data. If you set it once, don't change it again. Scoped values are a very good fit. If you have legacy code that uses thread locals, but it's used in a two-way fashion, or you change it a lot, it will be very hard to migrate it. So I wouldn't advise you do that. And thread locals are still supported, right? You just have to watch out when you use them with virtual threads. If we summarize this one, thread locals do not limit mutability and perform badly with many threads and also with virtual threads. But scope values support immutable values. They come with a strictly defined lifetime and can be inherited efficiently through structured concurrency. So practical implications, how will these features change your day-to-day life? Well, that depends on the kind of Java developer that you are. If you're a developer advocate or a trainer, you can just get started, try them out, talk about them like I'm doing right now. If you work on a framework or a library, probably you would want to start using them because you will probably have some concurrency features that you use directly, but beware of the preview status because a preview feature is always impermanent, right? And the Java team may decide to remove parts of it. So make sure to keep that in mind when you start using these features. So start using them, but keep in mind that only virtual threads are finalized right now. Structured concurrency and scoped values still have to be finalized, and they're both in preview. If you're a Spring developer, I don't think you would create threads yourself typically because it's done by the framework, but you can configure the Spring simple task executor to use virtual threads. Actually, this configuration will become a bit easier in the future because it will gain a method set virtual threads scheduled for Spring 6.1. You can set it to true, and then it will use virtual threads by default. If you use Jakarta EE, you can replace existing managed executor services by a managed executor definition like this and set virtual to true to get an executor service with virtual threads. That is a managed version. And you can also even use structured concurrency if you want with an overloaded structured task scope constructor that passes a managed thread factory that is known to the Jakarta EE container. And if you're a Quarkus developer, you can use the @run on virtual thread annotation on an annotated method to make it run on a virtual thread. We haven't come to journey's end. There are a few things in the works. Sharing streams of data among threads is mentioned in the JEPs. So other languages call this channels, specific mechanism to share data among threads. And a new thread cancellation mechanism that has been talked about. I'm not sure when they will start work on it, but it has been mentioned before. And solving thread pinning, one of the drawbacks of virtual threads, is definitely on the table. I haven't seen it targeted to a Java version as of yet, but I'm quite sure that will come. Before we get to Q&A, I quickly want to share this slide. The slide deck is available on my website, and also all the code that I showed you is in a GitHub repository. So if you want to play around with it, please make sure to clone that repo and see if you can put these features to the test. We maybe have time for 1 or 2 questions if there are any, so feel free to ask them if you have them.
There's one question in the chat.
Yeah.
How to cancel tasks externally in case of structured concurrency.
So you could still use the currently known interruption mechanism, right? Interrupt threads that we do usually. Make sure you catch that exception again. This might change in the future, right? Because they're thinking about new cancellation mechanisms. But this is the way that you should do it when it's up to me. And of course, if you used the shutdown on failure mechanism, you can simply interrupt your thread by throwing an exception. I think that would be the best thing to do if it is thrown, if it terminates exceptionally. I see someone asking me to share the slide link again, so I'll just quickly change the slide to this one, so you can see it for yourself. If it helps, I can also post it in the chat. Right, that's quickly done. Here we go. Just have to put HTTPS in front of it, but you'll manage. Was there another question?
There was one more question.
Yeah.
How do we control the number of virtual threads to avoid resource abuse?
Right. I don't think you can actually, Andres, but it's a good question. I think you can rely on the scheduling of the JVM, and also the JVM will decide how many threads to keep alive and how many to keep in the pool or discard. And because the creation and discarding is very cheap and very quickly done, we don't really need to control the number of threads anymore like we used to in the past. So that will be my answer.
And then we have one last question. When tasks are stopped, if one failed, do they receive interrupt, etc., to understand that they are or will be stopped?
That is a good question. So they will receive an interrupt. Yeah, they will receive an interrupt. But like with all things concurrency, it's very hard to predict when it will happen exactly, right? It is up to the scheduler, but they will receive interrupts, right? And I see a clarification from Andres here. If we want to control the number of concurrent database queries, I understand your question a bit better now, Andres. And I would say I would, for example, use a semaphore to keep track of how many connections there are to your database. They will still work perfectly fine with virtual threads. Okay, no problem, Andres. I think we're out of time, but I really enjoyed giving this talk and interacting with you. I've shared my social handles, so feel free to DM me there if you've got any more follow-up questions, and I will gladly answer them. And let's connect over there.